Hello everyone, welcome back to the lecture series of Learning Theory of Automata and Formal Languages. My name is Binayak Parashar. I am working as an assistant professor in the Department of Computer Science and Engineering at Ajay Kumar Garg Engineering College. So we have covered up a lot of things regarding this subject, and we have covered up regarding the finite automata concept in a proper way in unit number 1, where we have almost covered 11 lectures, and if you have not gone through them, you should go for those videos also so that you can relate with this lecture. So this is lecture number 14, and we will be discussing about the concept of how we can use a particular algorithm which is known as Ardens Theorem in order to convert a given finite automata to a regular expression. So this is actually unit number 2, where we are studying about the regular expression concept, as well as we are also studying about the regular language concept. But we haven't covered the concept of regular language in a proper way, because that is what we are going to study in the upcoming classes, upcoming lectures. Because in that particular video, we will try to understand how to identify that a language is regular or not. Because with the help of that only, you'll be able to identify that whether that particular language is accepted by a finite machine or not. Because regular language is the language which is accepted by whom? Finite automata. Clear? So this is all about a basic introduction of what we have done till now. Now, in this particular video, we will try to look into the concept known as the algebraic method using Ardens Theorem. Okay. So basically, first we will try to check what are the basic identities involved in the case of regular expressions. Whenever we talk about expressions, some of the other we come across with identities also. Okay, so we will try to look into that as well, and we will check that how these identities help in order to solve a particular question, like how to convert a finite automata to a regular expression. Okay, so let's check what this Ardens theorem is all about. Actually, if we talk about regular expressions, we need to find out some sort of simplification of those expressions. In order to simplify a particular expression, we use a concept, or we use a model which is known as Ardens theorem. How? Let us discuss that. Let us assume that we are having two expressions, P and Q. These are two regular expressions, and some way the other we come across with an expression like this: R is equals to Q plus RP. Then, according to Ardens theorem, this expression has a unique solution which is known as R is equals to QP star. R is equals to QP star. That means this particular part will be simplified into QP star. So some way the other we are trying to optimize the particular regular expression, and that expression should not contain, it's mentioned over here, that expression should not contain any sort of epsilon over there. If there is an epsilon, means what? Null. So that means we are not considering that expression some way the other. But if we find out an expression in this format, R is equals to Q plus RP, then it will have a unique solution, that is R equals to QP star. That is the general definition of Ardens theorem over here. Okay. So now that means whenever we get any sort of equation in the form R equals to Q plus RP, we will directly replace that by R is equals to QP star. So this is what the Ardens theorem is all about. Let's check what is its usefulness in the upcoming slides. Now, these are few of the things that I have brought across over here. Okay, just give me 1 second. Okay, now this is some of the identities that we will be discussing over here, and these are the identities with the help of which you can simplify a particular regular expression. Okay, now here always remember, while we talk about expressions, this this phi is represented by 0, and this epsilon is represented by 1. This is very, very important from your solve part or solution part or simplification part. Why? Because phi means what? Null, nothing. That means what? It is having this kind of representation. That means only an initial state. There is no final state, nothing string, nothing transitions, no inputs. That means this is what? A 0. And whereas we are having this initial as a final. That means some way or the other this will result or this will give an output which is having no input, no transition, but yes, we can say that yes, some or the other we can accept an empty transition for which it is represented by epsilon and whose value can be considered as 1. Correct? So this is a default value which we can say 1, and this is what initial state only. So that's why we have considered that it is a 0. Correct? So this is a little bit of explanation which I thought of like discussing with you all. Now in order to remember this thing, that's why I have told you phi is represented as 0 and epsilon is represented by 1. Now if we take these two values and put into a regular expression, suppose I am having a regular expression r, if we add a 0 to it, then we will get the same expression r. So you can remember in that way. Okay. If we do such kind of operation like phi multiplied by r or phi concatenated by r, this is nothing but what? Concatenation operator. Phi concatenation operator with r product with 0. What is the answer? 0 only. Correct? If we product the regular expression with the phi, then also it will give you 0. Next, same way, in place of phi, if we use epsilon, that means 1, then we will get what? R into 1, R. Correct? Similar way, epsilon to the power clean closure, 1 to the power clean closure means 1 to the power infinity. Always results as what? 1 only. Then phi to the power clean closure means phi to the power infinity screen. It will give you what? 1. Something to the power 0, it will give you as 1. So that's why it's coming as epsilon. Next, r plus r, regular expression plus regular expression will give you what? A regular expression only. This is a primitive expression. Correct? Next comes r to the power clean closure dot r to the power clean closure. This will resembles what? The same expression. Correct? Because you are trying to concatenate two expressions which are having infinity power. Definitely you will get the expression which is having infinity power. Correct? Next, this is an important one which you can remember, and I have also discussed with you all regarding this while discussing about operators. Suppose I know that what is the meaning of plus. Plus means what? It will start from r to the power 1, r to the power 2, r to the power 3, and it will keep on increasing. Correct? If we talk about r to the power clean closure, this means what? R to the power 0, r to the power 1, r to the power 2, and it will keep on increasing. Only 0 is missing in the case of r to the power plus. So what we can write? R to the power plus we can write as what? R dot r to the power clean closure. That's it. So this is the basic expression. R to the power plus equals to r dot r to the power clean closure. So whenever r to the power 0, then it will give you r, single r, which is nothing but what? This one. Clear? So next expression is r to the power clean closure to the power clean closure. Definitely it will give you clean closure only. Correct? Whatever you take a value, infinity only, it will give you infinity values only. Correct? So these are some of the expressions which we have seen, the basic identities. You can see 1, 2, 3, 4, 5, 6, 7, 8. 8 identities you have seen. Now let us check it out, some of the important identities which will help you in solving some of the expressions. Like first one, epsilon is nothing but 1 only. Epsilon plus r to the power clean closure, or epsilon plus r to the power clean closure will give you what? Result as r to the power clean closure only. Okay, so this you need to remember, because r to the power clean closure, some or the other we will get what? R to the power, what is the meaning? See, you have seen here, r to the power clean closure will what? R to the power plus. So r to the power plus some kind of 1 will give you what? R to the power clean closure. So that's why we can take this expression as a whole. So this is an important one, you will come across with this particular part. Next comes p dot q to the power whole clean closure dot p is equals to p, and then you can, this is nothing but one kind of associative one, right? So we can just concatenate q with p, and then we can put it into a clean closure. So these two are equivalent to each other. Okay. Next comes p plus q whole to the power clean closure. This we can write in this fashion. Okay, p plus q whole to the power clean closure. Now, why I have discussed this particular question while discussing about the diagrammatic representation of a finite automata from a regular expression. See how I have drawn like this. Now, what is the meaning of this? Meaning of this is what? P plus q whole to the power clean closure. So can we draw like this? Can we draw like this? That we are having a state, okay, and we are having Because this means what? This means what? P and Q are having a self loop coming out of this state and going into the same state. Correct? So what we can draw, we can take one more state, okay, and we can do like this, see? Okay. So if we can draw in this fashion, some or the other, we'll be having over here P and then a P, okay, and then Q and over a Q, okay, and some or the other we can have P to the power clean closure dot Q to the power clean closure, and it will act as a self loop, and overall we can say that P clean closure dot Q clean closure whole to the power clean closure, and which is the meaning of this expression. And the same way, if we do the same operation in the same way, okay, like this, okay, what is the meaning of this? P to the power clean closure. So I will take one more state and I will do P to the power clean closure over here, okay, and I am doing Q to the power clean closure, right? So I will be doing one more state and I will be having over Q to the power clean closure. Now what is the meaning of this? P to the power clean closure and Q to the power clean closure whole to the power closure. So that means some or the other we are trying to enter into this state, okay, and this is making a loop type. Okay, so some or the other we can having the same concept over this state. So this means what? P to the power clean closure by Q to the power clean closure whole to the power clean closure. So some or the other, this particular concept, that is this one, resembles both the cases. Okay, so this is also a very, very important concept. Okay, next comes this one, P plus Q whole to the power R. So this is also one of the like this is, you know, like A plus B. We do in mathematics also, A plus B into C. How do we write? AC plus BC. So this happens in the case of regular expressions also. So that is number 12 number expression. And last expression I have added, and that is nothing but your basic identities only, which is nothing but Ardens theorem. This particular topic we have discussed over here. So this is all about your basic identities. I hope you have I have tried to make you understand all these properties, and you need to remember a little bit by doing a little bit of practice over it. Okay, so let's now check next particular question, and based on the identities, this is what they have asked for. Okay, now we need to find out a particular solution, so some or the other, how to find out this left hand side is equals to this one right hand side. Okay, how to do that? In this kind of basic identities, you need to find out a particular similarities over here. If you look properly, this is one part and this is another part which is having the same expression. If you look into this, correct, and if you look into this one and this one, I think both are same, correct. So that means some or the other we are having a good thought that yes, we are having similarities. Now we need to check in the right hand side part. Right hand side part, see which is the given expression. This is the one which is not changing. It is representing in the same way. So this is what? This is nothing but this expression only, correct. So leave as it is. So that means this particular thing, these two expressions, we no need to do anything. We just need to manipulate with these two things. This is my first analysis. Okay, now let me do it. Let me first erase all the things and let me do it in a clear way. What I will do, I will try to do one thing, that I will try to solve this. How? I am taking the left hand side. Okay, I will take 1 plus 0 0 to the power star 1 as a common from this entire expression. So what will be the answer? The answer will be C. This means what? Epsilon. Epsilon means what? 1. So this into 1 will give you this expression, plus what is the result? This is the result, right? So I can write down as 0 plus 1 0 whole to the power clean closure 1 whole to the power clean closure into 0 plus 1 0 to the power clean closure 1. So I am done with the first initial step. Now I think we can go into one particular identity which is known as this one. Epsilon plus r to the power star results what? R star. Let me explain to you. Epsilon plus, if we take this as r, then what is the meaning of it? Epsilon plus r to the power star r, result will be what? R star. I hope now you can understand where I am utilizing these identities. So this will be what? R star. Correct? what is the meaning of R over here? R is what? R is this one, 0 plus 1, 0 to the power star 1 whole to the power star. Now let me go back to this. I have got this part. 0 plus 1, 0 whole to the power star 1 whole to the power star. See, 0 plus 1 whole, 0 to the power star 1 whole to the power star. So I need to just manipulate with this particular expression. How do we do that? It's very easy. We will take one common from here. So it will be your epsilon plus 0, 0 to the power star. And here it will be the same one, 0 plus 1, 0 star 1 whole to the power star. So if I do this expression as the same way, identity number this one, 9. So it will be what? 1 dot 0, 0 to the power star. Correct? This is what? Oh, sorry. 1 dot 0 star. I made a mistake. 1 dot 0 star. And whole multiplied by 0 plus 1, 0 star 1 whole to the power star. I hope we got the final right hand side of it. This is the entire question solution for it. Got it? So you just try to find out what are the similarity expressions over here and what is the similarity portion in the right hand side as well. And then you try to solve it. Okay? And how do you solve it? By using any of these identities. Okay? So let me erase this and let me showcast the entire work. This is your entire work. I hope the same way I have done with mentioning the basic identity where I have used, how I have used, and then you can note down this point. Okay. Let's go into question number 2. It says prove that the following regular expression this also describes the same set of strings. Same set of strings means what? After simplifying the regular expression, you will be getting the same set of strings. If you look into this expression, 1 is one expression and 0, 1, 1 is another expression. So how to do that? Let me check it out. I will take this as a regular expression given, okay, and I will make this one as P, and definitely, see, I have mentioned over here, see, P is nothing but this expression. Therefore, it will be what? Epsilon plus P, P to the power clean closure. And according to basic identity number, this one, what is the meaning? Epsilon plus R, R to the power star will give you R star. Correct? So that means what? It will give you P to the power star. So that means what I can write? P means what? This only. So same expression, I got it. Now if you look properly, I can write 1 as M and 0, 1, 1 as Q. Two expressions, right? One is M and Q 0, 1, 1 is represented by Q. So it becomes like this: M to the power star, Q to the power star, whole to the power star. And we know by basic identity number 11 that P plus Q whole to the power star means what? P star dot Q star whole to the power star. So using that identity, what we can do? We can write the M to the power star, Q to the power star, whole to the power star, we can write down as M plus Q whole to the power star. And this means what? 1 plus 0, 1, 1 whole to the power star. This means what? Okay, this will be only M, okay? This will be only M, only 1, okay? This means what? I got two things into this means what? This means this only. We are having an input state, okay, where we are having two things, 1 and 0, 1, 1. Correct? 1 and 0, 1, 1. That means the regular expression, this also describes the same set of strings. That means 1 and 0, 1, 1. That's it. This is how you need to prove it. I hope it is clear to everyone. Now we will check it out, the final part of our today's session, and we will try to find out how to find what are the properties involved in the case of regular sets, okay, or regular expressions. Basically, we have discussed these things in your earlier videos only, where we discuss about the properties of finite automata. We have discussed about the properties of the closure properties and decision properties. The same way the other we will be discussing about it. Okay. So we will try to find out the union. The first property is nothing but the union of two regular sets is always a regular. This concept we have already seen. That is nothing but, if you go back to the basic identities, see, I have already mentioned that union of two regular expressions is giving what? A regular expression. So this has already been proved, but already been discussed, but the proof is like this. I have taken one regular expression in this fashion, and I have taken one more regular expression in this one. Okay, and what these mean, like the first regular expression meaning is what? A whole to the power star. If star is equals to 0, then it will give you what? A. If star is equals to 1, then it will give you what? 3 times A. If star is equals to 2, then it will be giving us 5 times A. So it is keep on increasing, right? Language 2 says that A whole to the power star. This means what? If star becomes 0 here, if asterisk becomes 0, then it will become what? Epsilon. If 1, then A. If 2, then 4 times A. If 3, then 6 times A. Now, if we submerge these two things, it will give you a particular regular expression only, which is nothing but this one. Correct? And this is nothing but what? This is nothing but A. Therefore, for this language, we can make a finite automata, and therefore, this is a regular expression. And finally, we can say that the union of two regular sets gives you a regular expression. Clear? So, this is all about property number 1. Property number 2 says that the intersection of two regular sets is always a regular. We have discussed about it, that the same concept if you take and you need to try to find out the intersection of these two things, then somebody other will be getting a regular expression only. So, union also accepts, intersection also accepts. Let's take the next expression. The next expression says that the complement of a regular set is a regular. Let me explain to you. Let me take a string of even length. That means language will be what? 0, 2, 4, 6, 8 and so on. Correct? So, if you put a regular expression number 1, what it will be? It will be like this: A plus B whole to the power clean closure. If clean closure is equals to 0, then it will be what? 0, which is resembling this one. If it is 1, then it will be, sorry, this is not the exact way of writing it. Okay, you need to use one more part because I have to take length is equals to 2. Now, overall, here you have to mark it as epsilon, asterisk, sorry. If asterisk value is 0, then it will be 0. If asterisk value is 1, then it will be 2, correct? Length equals to 2. If asterisk value is 2, then it will be length equals to 4, it will be double. If asterisk value is 3, then it will be 6, then 4, 8, and it will keep on going on. Correct? So, this is the final expression we have got it. Correct? Now, if we find out what are the complement part of it, we will be getting language of this format: length 1, length 3, length 5, length 7, length 9 and so on. And the expression will be what? Expression will be like this: A plus B into A plus B into A plus B, okay, whole to the power asterisk. So, this will give you, if asterisk value is 0, then it will be length equals to 1, 1, then 3, 2, then 5, then 7 and keep on going on. That means some or the other, if we take the complement of this expression, we got a regular expression. So, that is why complement is also closed under the regular sets. I hope it is clear. Now, few more queries are there, like idempotent law, left distributive law and right distributive law. Now, what is the meaning of idempotent law? Idempotent law is just this one. If the same expression union with the same expression, you will get the same one, then that is said to be idempotent law. See, regular expression added with the itself, it will give you what? The same regular expression. Next comes left distribution law. Left distribution law says that if you do like this kind of operation, then it will result what? Lm plus Ln. It's somewhat similar to what we have discussed about this property. This one, P plus Q whole to the power R. It's actually R is on the right hand side, so it will become right distributive law. But if we put R on the left hand side of this, it will become what? Left distributive law. And that is what it is being mentioned over here, left distributive law. L is one expression and R is M plus N. So, if we plus it, L into M plus N, then it will come. Plus means what? We are trying to combine. We are not trying to union it. Okay, we are trying to combine both, then it will become Lm plus Nn. And if we do this operation in the right hand side, see, then it will give you what? M plus N whole into L will give you what? ML plus NL. So, this will give you the operation which is known as right distributive law. So, overall, if you look into the properties of regular sets, we got union, we got intersection, we got complement, we got idempotent law, we got left distribution law and right distribution law. So, these are overall properties of a regular sets. So, hope we have tried to understand in this particular video about the basic concepts about what is the basic identities involved in the regular expression part. We have seen the concept of Ardens theorem. Now, I just want to stop here and I will just let you know one more thing, that we have tried to understand this theorem, but we haven't applied right now. We will be applying this theorem when we will be trying to convert finite automata to a regular expression, which we will be seeing in the next video. Okay, in the next video we will try to learn how a particular finite automata can be directly converted to a regular expression with the help of this Ardens theorem. Okay, but as of now in this video we have tried to understand what are the basic identities. We have tried to understand this question, a solution of this question. We have tried to understand another question where we have tried to prove that the expression, the original expression, after simplification we got the same set of strings. Then we have tried to understand what are the properties involved in regular sets, that is nothing but union, intersection, complement, idempotent, left distributive and right distributive. Okay, so I hope we have tried to cover up all the things. If you have any questions regarding the or queries regarding the regular expression part, I would suggest that please go through lecture number 12 onwards, because from lecture number 12 we have started off with unit number 2 till lecture number 11 we have covered up unit number 1. In the next lecture we will try to find out that how we use this Ardens theorem in order to convert a particular finite automata to a regular expression. Okay, so thank you for watching this video.